quiz 17.1 deals with buffer solutions. And question 1 gives you a number of acid-base conjugate pairs, and we're supposed to look for the pH range where this buffer can act. And that would be pH equal to the pKa for the acid in that pair, plus or minus 1. And the pKa, of course, is the negative log of the Ka. And we can go to appendix A.3 for Ka values for most of these, but I want to point out the first one here, ammonium ion and ammonia, and this last one, HC5H5N plus and C5H5N. Both of those are nitrogen-based bases, and so in that case, what you'll want is the Ka is equal to Kw divided by the listed Kb value. So you'll find those two bases, NH3 and C5H5N, in the second half of appendix A3, and you'll find their Kb value. We still need the Ka value for their conjugate acids, and so Kw divided by Kb gives the Ka. And then once you have those Kas together with the Kas for our others here, then you can find the pKa, and then the pKa will just be plus or minus 1. For this hydrogen phosphate, look up phosphoric acid in appendix A3, and this is the third proton lost in that triprotic phosphoric acid series. And so you'll find phosphoric acid, it'll give you Ka1, Ka2, and Ka3, so that's the phosphoric acid, the third one here. Anyway, that was surprisingly complex, but hopefully you can sort of navigate appendix A3 appropriately now. So for NH4 plus and NH3, the pKa is 9.26, so we get 8.26 to 10.26 for the ammonium ammonia. For chlorous acid and chlorite ion, the pKa is 1.96, so you get 0.96 to 2.96. For the hydrogen phosphate and phosphate, the pKa is 12.32, so we get 11.32 to 13.32. And then finally, I can't remember what this is even called. It might be pyridine, I can't remember, but this other nitrogen-based base, the pKa is 5.23, so this would be 4.23 to 6.23. Those are the ranges where these buffers will work. Oops, wrong way. Okay, now we have 1.5 grams of magnesium fluoride are dissolved in a 100 milliliters solution of 0.5 molar hydrofluoric acid. I'm going to give myself as much board space as I can here, because I think we'll need it. And so the system we have here is the HF, F minus, right? Those are your acid and base pairs. And we can look up the Ka of HF in that appendix A3. And the pKa is going to equal 3.20. 3.20. And we'll use the Henderson-Hasselbalch equation here. pH is equal to pKa plus the log of, and I'm just going to put base over acid. And this could be the concentration of the base over the concentration of the acid, or it could be the number of moles of base over the number of moles of acid. So I actually kind of like to write it in this form because I think it's versatile. And either of those would work. In this case, it makes perhaps the most sense to do number of moles. So let's figure out how many moles of acid we have. So we have 100 milliliters, that's 0.100 liters. And the molar concentration is 0.5 moles per liter. And this is going to give us 0.05 moles of HF. Now for the base, we need to look at the grams of magnesium fluoride. So 1.5 grams of MgF2. This is a good old-fashioned dimensional analysis problem. You'll want to look up the molar mass of MgF2. It should be 62.30 grams of MgF2 is 1 mole of MgF2. And then 1 MgF2 is going to yield 2 F minuses. You know, that 2 in the formula matters. And so we're going to get 2 fluoride ions for every 1 magnesium fluoride formula unit. And so this is going to be a 0.048 moles of F minus. They're quite close to each other, so we should hope that the pH we calculate is pretty close to the pKa, maybe a little bit lower because we've got slightly more acid moles than base. So let's put it in there. pH is going to equal the pKa of 3.20 plus the log of base over acid. That would be 0.48 over, 0.048 over 0.050. So 3.2 plus the log of 0.048 over 0.050. And to be honest, when I put this in my calculator, I just did 48 over 50 because it's just the ratio that matters. Okay, so and we end up with a pH of 3.18. Technically, you should only get 1 sig fig, I guess, for the 1 molar hydrofluoric acid, but I meant to give you more sig figs. That was just a mistake. So 3.18 is the sig figs we'll put on the key. Question 3, find the pH if 25 milliliters of 0.75 molar hydrochloric acid are added to the buffer solution prepared in question 2. I'm actually going to erase this. Everything we need is kind of contained up there, just as long as we remember what it represents. And I actually didn't show you how to solve this sort of a problem, not explicitly at least, in the lecture, so pay attention. We're going to be doing these sorts of tables a lot in the coming sections as we talk about titrations and things. But what I'm going to do is write the chemical reaction that will occur if I add hydrochloric acid. That would be HCl, and it's going to react with the F minus. And that is going to form HF plus Cl minus. And now I'm going to make a table that's going to look exactly like an ice table, but I'm going to call it a BCA table. And the only reason I do that is to emphasize that this table does not have an equilibrium arrow. This table goes to completion. And for an ice table, ICE stands for initial, change, and equilibrium. This stands for before, change, and after. And so let me show you how we set it up. How much hydrochloric acid moles do we have? Well, 0.025 liters of hydrochloric acid times 0.025 0.75 molar. That means we have 0.0188 moles of HCl. That's based on the amount that we added. So I'll put that in before, 0.0188. How much fluoride do we have? Well, that was the 48 millimoles, or 0.048, 0.048. How many moles of hydrofluoric acid? That's the 0.050. And chloride I don't really care about, so I'm just gonna draw a line through it because it's not actually relevant to this. And so we'll make a table just like an ice table. This time the change is going to be the limiting reactant. And at a glance we can see we have less hydrochloric acid. And so we're going to react all of the hydrochloric acid. And we will react a similar amount of the fluoride because we have a 1-to-1 stoichiometric ratio. And we will gain that amount of hydrofluoric acid. So do you see that? This change amount came from the amount of hydrochloric acid we added. It's going to react until there's no hydrochloric acid left. There's 0. And then we'll have a new amount of fluoride. Looks like 0.029 moles. And we'll have a new amount of HF, 0.069 moles of HF. And now we have new amounts that we can put back into the Henderson-Hasselbalch equation to find the new pH. So here's pH is equal to the pKa of 3.2 plus the log of, now our base is 0.029 and our acid is 0.069. These new numbers go into the Henderson-Hasselbalch equation. Let me stand back a little bit and let you see that. That's the base, 0.029, and there's the acid, 0.069. And this gives us a pH equal to 2.82, which I think is a very modest change considering we put a decent volume of a decently concentrated strong acid into our solution. And I didn't ask this on the quiz, but let's consider what would be the pH change if we put 25 milliliters of 0.75 molar hydrochloric acid into 100 milliliters of water instead of into 100 milliliters of this buffer solution. Let's figure out what the pH would be. What we really just need to do is take this molar concentration and perform a dilution. So our diluted concentration is going to equal 0.75 molar times the 25 milliliters divided by the new final volume of 125 milliliters. And this one I actually have not worked out ahead of time, so let's pull up the calculator here. So we'll have 0.75 times 25 divided by 125. Okay, so that is the new concentration of hydrochloric acid after we've added the 25 milliliters of hydrochloric acid to 100 milliliters of pure water. And we can just convert that into a pH by taking the negative log of 0.15. And it looks like the pH would have been 0.82. Would be 0.82. 0.82. Okay, so you can see how the buffer, was it 82 exactly? Cool, okay. So the buffer prevented a change of 2 pH units. Instead of going all the way down to 0.82 from 3.18, it only went down to a measly 2.82, which is less than half a pH unit instead of nearly 2.5 pH units. Good job, buffer. Okay, let's go back here to question 4. So question 4 says you want to make a buffer solution with a pH equal to 9.75 using a hydrocyanic acid buffer. You have one solution with HCN of 0.1 molar and another with CN minus of 0.2 molar, which you can mix together to make the buffer. If you start with 125 milliliters of the HCN solution, how many milliliters of the CN minus solution should you use? Okay, so this is just a different way of creating a buffer. And there's actually 100 different ways to make a buffer. So I don't apologize for showing you 2 different ones on one quiz. And you should really realize that it all comes down to that ratio of base over acid. And you know, I could have 2 solids that you add to pure water, 2 aqueous solutions, 1 aqueous solution and 1 solid, like we did in question 2. You can also start with pure conjugate acid and react some of it with strong base to generate some amount of conjugate base. There's all sorts of ways. So anyway, this is what we want. For HCN, pKa is equal to 9.208. Okay, and we want a pH of 9.750. So let's just do the Henderson-Hasselbalch equation right away. 9.750 is equal to 9.208 plus the log of base over acid. And we'll just kind of leave that in its generic form for now. Well, we can subtract the 9.208 from both sides, and we end up with log of base over acid is equal to 0.542. And then we'll raise 10 to that power. And we end up with that ratio, base over acid, is equal to 3.48. Okay, well now let's deal with the base over acid. There are, again, a number of ways that you can solve most problems. I feel like the easiest way is to consider the moles of the base, and the moles of the base is going to be the concentration of the base. That's 0.200 molar times the volume of the base. And the moles of the acid is going to be the concentration of the acid, 0.100 molar, times the volume of the acid, which was 125 milliliters. Now this, you can solve. That's not so bad. VB is going to equal 3.48 times 0.1 times 125 divided by 0.2. And that is 218 milliliters. That's the volume of the base. Okay. Now question 5. Find the buffer capacity of the solution prepared in question 4. And we're going to do it the easy way. That is just how many moles of strong acid or strong base could be added before all of the buffer reactants are consumed. So what we really need to find here is just what is the number of moles of base and what is the number of moles of acid. Okay, well, we actually just kind of had those up. That would be 0.200 molar times the 218 milliliters. That would be 0.218 liters. And so that's 0.001 0.0436 moles of base. And that means that you could react with 0.0436 moles of strong acid before you ran out of conjugate base. And then for the acid, that would be 0.100 molar times 0.125 liters. That's the concentration and volume given in the text of question 4. And that is going to equal 0.0125 moles. That's how much conjugate acid you have, and therefore that is how much base you could add before you run out. So this would be acid added and base added. And that's all I wanted you to do, but I do want to show you finding the sort of ratio of 1/10 or 10 buffer capacity isn't as bad as you might think. So let's figure out N total. What is N total? That's going to equal the sum of those two. So that'll be 0.0436 plus 0.0125. Oh, sorry, you can't see what I'm doing. There you go. 0.0436 plus 0.0125. That is 0.0561 moles. 0.0561 moles. And then if you followed sort of the derivation that I did in lecture, and if you were thinking about it, you would have realized that what we'll call N capacity, that's the maximum amount of base you could have before you exceed that 10/1 limit, or the maximum amount of acid you could have before you exceed the 1/10 limit. That N capacity is actually going to be 10/11 N total. It's actually that easy. No matter what your N total is, that will be the ratio. So let's figure out what N capacity is. 10 divided by 11 times 0.0561. That'll be 0.051. 0.051. And so how many moles of base can I add before my amount of conjugate base reaches 0.051? So how much base can I add? Well, that's going to be 0.051 minus 0.0436. So that's 0.051 minus 0.0436. That's going to be really just 0.0074. 0.0074. And how much acid could I add? That would be that 0.051 minus this time the amount of acid that I currently have. Because as I add acid, we'll be increasing the amount of conjugate acid here until it reaches N capacity. So that's 0.051 minus 0.0125. That's going to be 0.038. 0.038 moles. Okay, so if we compare that to what my key says, our sloppy method said base added, I can add about 0.0125. Well, really, it should only be 0.0074. And our sloppy method said we could add about 0.0436 moles of acid. The better method says 0.038. So you see, this is truly a sloppy method. it can be off by as much as like, this is maybe closer to half of that value. So we overestimated the buffer capacity by almost double. So, and this method really isn't too terribly bad, so I thought I'd just show you how sometimes it would be worth it to go to the extra trouble. Okay, and that's it for quiz 7.1.